The exercise asks, given 8 spillway gates, each with a probability of 0.05 of not opening, what is the probability of 5 gates not opening? And what is the probability of at least 3 gates not opening? If you decide to complete the exercise using Microsoft Excel, I've included the formula on the slide.
Here's the solution. We have 8 spillway gates, so n equals 8. And for the first question, we want to know the probability of exactly 5 gates not opening, so k equals 5. P is equal to 0.05, so we can plug it into the equation I provided. K is the first term, n is the second term, P is the third term, and we type in false for the last term since we do not want a cumulative probability. We want the probability of exactly 5 gates not opening. This returns a probability of 1.5 times 10 to the minus 5. For the second question, we need to be careful and use a little critical thinking because the question asks for the probability of at least 3 gates not opening. To do this, we can calculate the probability of 2 or less gates not opening. Then, by subtracting the probability of 2 or less not opening from 1, we can get the probability of 3 or more gates not opening. So, we have 1 minus our binomial distribution function with k equals 2, n is still equal to 8, and p is still equal to 0.05. This time, we want to choose true, so the formula will return a cumulative probability, the probability of 2 or less not opening. From this equation, we get the answer to be 5.79 times 10 to the minus 3. Another way to answer the second question is to calculate the probability of exactly 3 gates not opening, and exactly 4 gates not opening, and exactly 5, exactly 6, exactly 7, and on up to exactly 8 gates not opening, and then sum those probabilities. You'll see that we'll get the same result, a probability of 5.79 times 10 to the minus 3. From this table, you can also see how the probability is drastically lower when more and more gates are assumed not to open. Practically, when doing a risk assessment, you can use these results to prune branches from the event tree, such as the 7 and 8 gate failure scenarios, because of the remote probabilities. The probabilities for the 7 and 8 gate failure scenarios are so low that they will have a negligible contribution to the total project risk. To make things a bit easier, the RMC's event combination toolbox can be used to assess the probability of k or more gates failing, or exactly k gates failing. Here's the solution to the previous exercise using the identical probabilities worksheet from the toolbox, since each gate has the same probability of not opening. Simply input the probability of a single gate failure P and the total number of gates N in the yellow boxes, and the spreadsheet will do the rest. In the previous example, each gate had the same probability of failure. However, if each gate has a unique probability of failure, it gets more complicated. Each scenario must be accounted for. The Unique Gates worksheet in the RMC's Event Combination Toolbox can be used to assess up to 6 gates, each with a different or unique probability of failure. Failure probabilities are highlighted in red, and the unhighlighted values are probabilities of not failing, 1 minus the failure probabilities. In this example, there are 5 gates, and each gate has the unique probability of failure shown in the top row. To obtain the probability of 1 gate failing, the calculations are shown. The probability of only gate 1 failing is obtained by multiplying the probability of gate 1 failing by the probability of each of the other gates not failing. The process is repeated for each of the other 5 gates, and the results are summed. The solution from the toolbox is shown in the summary table at the bottom right.